Hello, everybody. My name is Masoud Olia, and I'm a professor here in School of Engineering at Benford Institute of Technology, and I'm back again with another example of static problem. Currently, I'm teaching statics at Wentworth, and I thought maybe we should look at the three-dimensional particle equilibrium problem. Okay, so what I'm going to do actually, I'm going to remove my video so you don't get distracted, so I can flatten my tablet so I can write better. So let me do that. Sorry, guys. Here we go. So as you can see from the statement of the problem, our goal is to find the tension in cables AB, AC, and the force developed along the strut AD. So basically AD acts like a cable here. And then of course the load that is being supported by these, in a way, three cables is 400 pounds. So like any problem that be particle equilibrium or rigid body equilibrium, the most important thing in getting the problem started is drawing a free body diagram. So why don't we start by doing that? So I'm going to actually show my known 400 pound here, right? And we'll just draw the three forces, meaning the tension in cable AB, AC, and AD. So I'll use red for those. That's one. And that's one. So that's, I call it FAB, I call it FAC, and I call this FAD. Now, if we get positive for all these, the directions, okay. I mean, of course, the cables, they have to be in tension. Now, the strut AD could be in tension or compression. Here, I'm assuming that the strut actually is in tension, the way I'm showing that it's pointing away from the point A. Okay, so in this case, a three-dimensional particle equilibrium, we have three unknowns, right? AB, AC, and AD. And then we have three equations. Our equations are what? Sum of the forces in X equals 0. We have to balance forces in the X. We have to balance forces in the Y. And similarly, forces in the Z. So three equations and three unknowns, we are all set. So the way I'm going to balance these forces in X, Y, Z is first to describe each force vectorially in the Cartesian format, I, J, K. So I'm going to actually figure out the coordinates of different points here. So I'm going to start with A. I'll ask myself, what is the coordinate of A? We notice that A is at 0, 6, 2.5, right? Of course, D is right at the origin, right? 0, 0, 0. And then point B, as you could see, has a coordinate of -2, nothing in the Y, and 4 in the Z, right? And then point C, I'll put it here for you. Looks like we are a 2 in the X, right? Again, nothing in the Y, and 5.5 in the Z. All right, so we can now start describing each force vectorially. I start with AB. You guys know from other videos that I've had, or you've seen it in maybe other YouTube videos, that whenever you want to describe a force vectorially, you take the magnitude of the force. Of course, we don't know what the magnitude is. Remember, this is unknown, AC is unknown, and then AD is unknown. But then you multiply it by the unit vector along the line of action of the force. So let's go ahead and do that. What is a unit vector? Unit vector is basically a position vector divided by its length, by its magnitude. And to describe unit vector from A to B, See the line of action, this force AB is along AB. It's acting, from A to B. So A becomes the initial, B becomes final. So you subtract initial from the final. So -2 minus 0 gives me -2I, right? 0 minus 6 gives me -6J. And then finally, 4 minus 2.5 will give me 1.5 K. So when I go ahead to find the length of this, remember the length is 2 squared or -2 squared. It doesn't matter. -6 squared plus 1.5 squared. So that's how you make a unit vector. So the denominator of this guy becomes, let's calculate that. I didn't calculate that ahead of time. 36 plus 4, that's 40 plus 1.5 squared. So 40 plus 1.5 squared, of course, that becomes 42.5. What is the square root of that? So we raise this, okay, let's see. So that's 6.5. So this guy is 6.5. Okay. So FAB becomes, if you want to look at individual components, it's -2 over 6.5 FABI, right, as a vector. So that's the X component. -6 over 6.5 FABJ. And then similarly, plus 1.5 over 6.5 FABK. And we're going to do exactly the same thing for the other forces. So for AC, I'll do the same thing. So magnitude times the unit vector along AC. And similarly from A to C, A is initial, C is final. So subtract initial from final. So 2 minus 0, that's 2I. 0 minus 6 minus 6J. And then minus 5.5 minus 2.5, that's 3.5. Right? And what would be the magnitude of this guy? Again, this is the, I believe this one becomes 7, exactly 7, if I'm not wrong. Let's check. I'm a 5.5, I'm sorry, 5.5 minus 2.5 is 3. So let me clean this up for you. So that's 3K. I forgot to put the K value there. All right, so it becomes 7. So FAC vectorially is 2/7 FACI minus 6/7 FACJ, and then plus 3/7 FACK. All right. Okay, the next thing we want to do is describe AD in the vector form. So the same story. Remember that tension is that is it's like a 2-force member in tension or compression. FAD times the unit vector along AD. Right? So what is that unit vector, guys? Just again, final minus initial. So we have 0 minus 0, 0I, but I'm not going to even bother with that. 6 minus 0, 6J, right? And 2.5K, 2.5 minus 0. The denominator of this guy becomes, I believe, 6.5, the magnitude. So I'll write this like that, 6 over 6.5 FAD J and 2.5 over 6.5 FAD K. So now what we're going to do is just have the weight that we have to set it up to. Look, the weight, should have called this W here, is 400 in the negative Z direction. So vectorially, that's minus 400K. So let's go ahead and start balancing forces So in other words, just take the work on this equation, sum of the forces in x equals 0. So the x component of FAB is this guy. So we have minus 2 over 6.5 FAB, right? And we have the x component of FAC is right here, 2/7 of FAC. This guy doesn't have any x component, right? We just have J and K. And nothing in the weight doesn't have any contribution. So that's our first equation, right? I call it equation number 1. Then I'll do the same thing in the y direction, balancing forces. So as you could see, we have minus 6 over 6.5 FAB, right? Contribution of the FAC is what? Minus 6/7 FAC. And then the 6 over 6.5 FAD, right? I believe I made a mistake here, guys. See, when I did the UAD, right? So remember, A is the initial, D is final. So I should have subtracted, I should have had a minus 6 here, minus 2.5. Okay, guys, so just logically, that's the way it should be. So actually, when you look at this equation, guys, notice that it's interesting. One of these guys, you can't have all negative here. That's not going to be balanced. So one has to switch. See, these are tension cables. It's AD that has to switch direction, which means basically the direction of AD is wrong and it should be the other way, right? And that means that member actually happens to be compression. It will work eventually in the equations, guys, when you try to solve. So I'm glad that I picked that mistake that I made. All right, in the Z direction, guys, we have a 1.5 over 6.5 FAB, right? That's this guy right here, right? From AC, we have a positive 3/7 FAC. And then finally, we have this guy, after I corrected it, of course, minus 2.5 over 6.5 FAD. And don't forget the weight, which has Z component, minus 400 equals 0. So I guess I should have labeled this as equation number 2 and this one as equation number 3. So now you have to solve the 3 equations as you like. Now, some people might just do it by hand. You could actually use a substitution method, write FAC in terms of FAB and plug it into these 2 equations so it becomes a 2x2. And then 2x2 is easy to solve, right? Or you can make a matrix like I'm going to do for you here. So, and use program on your calculator or, you know, use MATLAB. So if you want to make a matrix, guys, here we go. So these are the coefficients of, see, it's order FAB, FAC, FAD. So for the Y, the contribution of AD is 2/7, nothing for in the first equation. So this is your first equation, right? Nothing from AD. And then we have a full row here. Minus 6/7 and minus 6 over 6.5. Finally, a 1.5 over 6.5, a 3/7, minus 2.5 over 6.5. By the way, when you go to MATLAB, you have a 0, 0. I'm going to take this guy to this side, so it becomes a positive 400. So you go to MATLAB, you can just watch a video on YouTube and see how to solve a system of linear equations, okay? And then if you solve, you notice that FAB and FAC have the right direction because remember, they're in tension. You have no control over that. But when you solve for AD, you happen to get a negative. It turns out that this becomes minus 547, which means you just have to change the direction, as I showed you here, the direction switches. So it's in, this member is in compression. Obviously, the two cables are in tension. So this guy is 295. Of course, these are pound. And this happens to be roughly 274 pounds. Okay. So I just want to show you a quick example. I will see you guys soon. As always, I appreciate if you, let me see if I could put my video back so I can, there we go. So as always, I appreciate if you like the video and subscribe if you like to see more videos on different topics. I do statics, dynamics, system dynamics, vibrations, mechanics of materials, and so on. Okay, thank you, and have a good day.